We will now study transformations of functions. So we model real-life scenarios using mathematics in the form of words, tables, graphs, and equations. One method we use is to adapt the basic graphs of the toolkit functions to build new models for a given scenario. The first transformation that we're going to study is to shift the entire graph either up, down, left, or right. These are called shifts or translations. Shifting the graph either up or down is called a vertical translation, while shifting the graph either left or right is called a horizontal translation. So given a function f of x, a new function g of x equals f of x plus k, where k is a constant, is a vertical translation of the function f of x. All of the output values are changing by k units. If k is greater than 0, then the graph is going to shift upwards. If k is less than 0, the graph will shift downwards. And over here we can see, here's the original function, x squared. If we subtract 3, you can see that it shifts downwards by 3 units. Versus if we add 3, we see it shifting upwards by 3 units. Given a function f of x, a new function g of x equals f of x plus h, where h is a constant, is a horizontal translation of the function f of x. If h is greater than 0, the graph will shift to the left. If h is less than 0, the graph shifts to the right. Again, we have the same graph, x squared. If we add 3 units to the input, you can see that it shifts leftwards 3 units. Because if we subtract 3 units from the input, you can see that it's shifting to the right 3 units. So let's go ahead and sketch the graph of the absolute value of x plus 1 minus 3. So let's start by drawing our axes. All right, draw 7 tick marks in all directions. Now I'm going to start by drawing the toolkit function absolute value of x. Now you should remember that that graph will look something like this. Not quite. Something like that. So let's call this graph absolute value of x. Now, Let's go ahead and subtract 3 from it. While subtracting 3, this piece right here, we'll shift it downward by 3 units. So now the vertex will occur there. And that's going to be the result. Well, now let's take this graph and deal with this +1 being added to the input. So that will shift it to the left by 1 unit. So the new vertex will be right there. And so that graph in blue is the graph of the absolute value of x plus 1 minus 3. So another type of transformation is a reflection over the x-axis or over the y-axis. A vertical reflection is a reflection that occurs over the x-axis, whereas a horizontal reflection is a reflection that occurs across the y-axis. So given a function f of x, a new function g of x equals negative f of x is a vertical reflection of the function f of x, whereas the function h of x equals f of negative x is a horizontal reflection of the function f of x. And over here we can see that. So this blue is our original function. If we reflect it across the y-axis, we have a horizontal reflection, and that is f of negative x. Right, so every input value just switches negative. Reflecting it over the x-axis is negative f of x. Right, that's this green one. Every input value is getting multiplied by negative 1. So we're going to write a function that represents a vertical reflection and a horizontal reflection of the square root of x. We will determine the domain and range of the new functions, and then sketch all 3 of these on the same axes. So for the first one, we wanted a vertical reflection. So the function is g of x equals negative square root of x. The domain is the same as f, so it's 0 to infinity, right? We're not allowed to have a negative under the square root. However, the range now would be negative infinity to 0, right? Because square root of x is going to give you all non-negative values. So if you multiply a non-negative by a negative, it becomes negative. For the horizontal reflection, our function is the square root of negative x. The domain of this now, again, we're still not allowed to have a negative under the square root. So x must be negative values. and the range would be all non-negative values. So now to sketch them, so start with the original function square root of x. Right, it'll start at the origin, and we'll wind up doing something like that. So let's look at negative square root of x next. Okay. So it's a perfect mirror image of square root of x, except it's now flipped over the x-axis. If we now look at the square root of negative x, again, it's a perfect mirror image of square root of x, except it is flipped across the y-axis. So we now have even and odd functions. So a function is called an even function if for every input of x, f of negative x is equal to f of x. The graph of an even function is symmetric about the y-axis. A function is called an odd function if for every input value x, f of negative x is equal to negative f of x. The graph of an odd function is symmetric about the origin. Right? So this part here, the f of negative x equals x, and the f of negative x equals negative f of x, is the algebraic way of determining whether a function is even or odd. The second part, the symmetry, is the graphical way of determining whether a function is even or odd. Now note that it is possible for a function to be neither even nor odd. So let's determine whether the given function is even, odd, or neither. So to determine which one it is algebraically, we want to take f of negative x. So we'll get negative x to the third power plus 2 times negative x. Right? Negative x to the third power is negative x cubed, and then minus 2x. Now we can factor out that negative 1, and we're left with x cubed plus 2x. But this is f of x, so we get negative f of x. So we can therefore conclude here that this function is odd. And if we look at its graph, right, you can see that this bottom piece here is a perfect mirror image of the top piece, reflected about the origin. So this is symmetric about the origin. If we now look at f of s is equal to s to the fourth plus 3s squared plus 7. Again, algebraically, we'll do f of negative s and see what we get. So negative s to the fourth power plus 3 times negative s to the second plus 7. So negative s to the fourth power is s to the fourth. Negative s to the second is just s squared. And then that plus 7 doesn't change. But this was f of s. So we can therefore conclude that f of s is even. And if we go and look at the graph, so this is the graph of f of s, you can see that it is a perfect mirror image across the y-axis. Finally, the last type of transformation is a stretch or compression. So if we're given a function f of x, a new function g of x equals a times f of x, where a is some constant, is a vertical stretch or a vertical compression of the function f of x. If a is greater than 1, then the graph will be stretched by a value of a. If 0 is less than a less than 1, so if a is between 0 and 1, then the graph will be compressed by a factor of a. And if a is to be negative, then what will happen is the graph will flip, right? So it'll be reflect off the x-axis, and then it will be either stretched or compressed depending on this. And we can see here, so this blue is our original function f of x. If we multiply it by 2, it stretches out in the vertical direction by a factor of 2, versus if we multiply it by a half, it will be compressed down in the vertical direction by a factor of 2. Given a function f of x, a new function g of x equals f of bx, where b is a constant, is a horizontal stretch or a horizontal compression of the function f of x. If b is greater than 1, then the graph will be compressed by a factor of 1 over b. If b is between 0 and 1, then the graph will be stretched by a factor of 1 over b. And again, just as with the vertical, if b happens to be negative, it will be reflected across the y-axis, and then will be either compressed or stretched based on these conditions. Right, so if we look, again, we have the function f of x. So if we multiply it by 2, or I'm sorry, if we multiply the input by 2, you can see that it's being compressed in the horizontal direction by a factor of 1/2, or it's being compressed by a factor of 2. If instead we multiply the input by a half, it is being stretched out by a factor of 2. So that concludes our discussion on function translation.